conclude this news, a special correspondent, Julian Blum, has realized a report about photovoltaic in the University of Milano.
First of all, I'm going to ask questions to Madame Guy to know what people think about energy problems.
Well, I have a dream in a world without violence, oil and pollution. I don't know if you're aware, but pollution caused by fossil energy is the main reason of the global warming.
I offer a solution, the photovoltaic panel. But what is it? I found a student specialized in the construction of the photovoltaic panel. He is going to explain it to us.
The photovoltaic panel is made of smaller components called cells. There are different types of cells, but all of them work the same. They are made of a semiconductor material called silicium. To make the panel weatherproof, it's covered with a glaze plate. This glaze must be as transparent as possible to minimize the reflection of photons on its surface. At last, the panel is placed in an aluminum frame in order to be easily manipulated. Once it is placed, the panel is connected to a junction box which gathers electricity produced by each PV cells.
We know what it's made of, but how does it work? Lucien, who is studying electricity, is explaining it.
First of all, we have to know that the photovoltaic cell can be divided into two parts. The upper ultra-thin surface anode and the lower p-load. To get the doped surface, a small quantity of other atoms than the silicium, which is the main part of the cell, are simply inserted in it. Some with more valence electrons in the n-type and some with less in the p-type. The n part contains just a net negative charge and the p part a net positive due to its lack of electrons, or said in another way, due to its positive holes. Now, when one type semiconductor is connected to the other, these electrons spontaneously travel to the p part and this hole to the n part. That particle displacement generates a huge internal electric field from the n part to the p part that will be opposed to these transfers. Now, when a voltage is applied to the cell, it can either cancel or increase this electric field. In the first case, the electrons move from the n part to the p part, while the holes do the opposite. Current flows thus in the cell like this, in this way. Sorry. But in the second part, only the small amount of holes in the n part and of electrons in the p part can pass the junction to make a small current nearly negligible compared to those in the first case. This is almost what happens in the photovoltaic cell when photons arrive on it. The photons give all their energy in the n part to create lots of electrons or pairs. And because of the electric field, forces are applied on these electrons in the hole, and first, so the electrons are repelled out of the cell, while second, so the holes are attracted towards the p part. We have just now a current proportional to the light intensity in our cell in this way. Oh yeah, and one last thing. Bear in mind that not every photon is allowed to create current in our cell. There is a minimum wavelength. Indeed, we've observed that there is no current below a certain threshold frequency regardless to the light intensity.
It's becoming clear, but there is still something I don't understand. Why is there no current in the photovoltaic cell below a certain frequency?
In the material, there are allowed band energy and forbidden ones at different intervals. For each band of energy, it contains a large number of energy levels proportional to the number of atoms in the crystals. Indeed, according to the Pauli's exclusion principle, there can be only one electron per orbital. Similarly, n atoms fill n energy levels until a maximum value called the Fermi level.
The bands of energy beneath the Fermi level are called the valence bands, and the band of energy that's above the Fermi level, so the first band, is called the conduction band. So when you have a metal, the Fermi level is in the middle, is in a conduction band, which means the band is not filled. There is still space for the electrons to move, and so that makes conduction possible. With an insulator, the Fermi level is in a forbidden band. So the bands are either empty, either full. So there is no space for the electrons to move and conduction isn't possible.
In our case, we use a semiconducting material, which is an insulating material, but the gap is small enough to be crossed thanks to an input of energy. This contribution is provided by the photon, which are a form of energy. The energy of a photon is given by this equation, where h is the Planck's constant and f the frequency of the photon. If the energy of the photon is smaller than the gap, the photon is deflected and unabsorbed. But in the other case, the photon is absorbed and then the excess energy here is given to the electron as a kinetic energy, and that makes the conduction possible. So, as a conclusion, for cells to work, we have to find the suitable material.
In the end, Jonathan is explaining the photovoltaic panel.
Future of photovoltaic is very promising. At the moment, the market growth is exponential and it should last. There are 3 generations of photovoltaic panels. The first generation is the one that you discovered in this report. In the future, panels will be of the second generation, which are cheaper, more malleable, but less efficient, and of the third generation, which are based on new technologies to improve performances.